Hello, bon dia. Today I'm going to talk to you about the hidden costs of chlorine dioxide. Let me introduce myself. My name is Tom Holm. I'm the Buckman Global Market Development Manager for pulp. So I'm responsible for all pulp applications internationally for Buckman Chemicals. I was born in Wisconsin, went to university there. I've been working in pulp mills since June 1st of 1982, so almost 39 years. While I worked in Hawesville, Kentucky, I was also involved in starting up some plants in the eastern US. I also worked as a technical resource for CO2 generators. I came to Buckman about 5 years ago from Hawesville, where I was the fiber line manager. And with Buckman, I've been in 23 countries working with pulp mills. I live in Tell City, Indiana, and you can see there my dog is helping me out making a little fire. So I got some numbers to think about as we go forward. 1.58, 21.1. As we go through, think about those numbers a little bit. First, a brief history of ClO2, because if we don't remember the past, we won't do the right things in the future. It's been around for a while, since 1814. It's been used in bleaching pulp since the 40s, but it was always used in the latter stages because it was quite expensive compared to chlorine. But in the 80s, about the time I came in, we found that chlorine caused dioxin as a byproduct in the effluent. And the industry spent a lot of energy and time getting that out. So what we did was we replaced it with chlorine dioxide and created what they call ECF, or elemental chlorine-free pulp. And it reduced the AOXs and everything was a big win. But during that time, they said, well, heck, if we can do that, let's see if we can get rid of chlorine altogether and go to TCF, or total chlorine-free bleaching. At the time, it did not gain widespread acceptance because it was more expensive and the pulp was not as of good quality. So today, almost all pulp is bleached with ECF, although here in Europe, TCF is beginning to grow. And part of that is the difference in quality and costs are still there, but there's a lot of new technologies that have helped reduce that gap. Enzymes, which is one that I'm particularly interested in, is one of those technologies. And what we run up against, and the whole reason for the talk today, is that we find that these new technologies are not fairly evaluated. And the reason that they're not is because many customers way underestimate what the real cost of their chlorine dioxide is. So we're going to talk about what is the true cost of chlorine dioxide. What does it take to make a kg of ClO2? Well, theoretically, if you go through the math, it takes chlorate, acid, and methanol in certain concentrations. And the math is quite simple then. You just take your cost per unit of chemical and add them up. It's that simple, right? It's so simple the child could do it. But the fact of the matter is it's not that simple. It's really not that easy. There is a credit that could be taken from the sodium and sulfur compounds that come out as byproducts from the generator if those materials are brought back into the process. Some places they are, some places they're not. That assumption of 1.58 kg of chlorate, that assumes 100% conversion. No plant is perfect, although these plants are very, very efficient when run correctly, and they can push 98, maybe even 99%. But there's others that I've seen efficiencies as low as 80%. We're assuming that all the ClO2 that we produce in the generator gets used in the bleach plant. We know that's not the case, because if that was the case, we wouldn't need the scrubbers off of the bleach plant to capture the fugitive gases. Those fugitive gases are chlorine dioxide. So we know that all the chlorine dioxide we make is not used. So we can assume other losses, and then there's leaks and spills and what have you. So anywhere from 5 to 20% losses in ClO2 are quite common. So what's the real chlorate usage ratio? Is it 1.7? Is it 1.9? Is it more? This is something that many mills don't really pay a whole lot of attention to. But there's more to it than just those costs. Then there's the energy cost. And this one many customers miss. Because we have to remember we're in a 1% solution of chlorine dioxide. So that means for every pound or every kg of ClO2, we've got a pound or 99 pounds or 99 kgs, depending on the system, of water associated with it. And that water has to be chilled and reheated. So if my math is right on the metric side, that equates to around 21 megajoule per kg of ClO2. That's a variable energy cost that has to be included. And there's fixed costs. And by the way, that the electrical cost, most of that is for chilling water. That is very expensive. Fixed costs, you've got all your pumps and drums, you've got operator time. They also have to unload chemicals, which is an exposure. And then we have the maintenance costs. And CO2 generators are very expensive to maintain because of the corrosive nature of the liquor that's used in them. Everything is titanium and very, very expensive, very specialized techniques need for maintenance. And in some places, there's a production cost. In the southeast of the US, in the summertime when things get hot, it's difficult for the mill to maintain enough chilled water supply to run the CO2 generator, and a generator will actually slow down the mill. And then there's the intangibles. There's the market demands, the environmental costs, the plant life cycle issues, and then most importantly, safety. When we look at customer demands for greener products, in Europe leads the world in looking at how do we make our processes greener? How do we have less environmental impact? And the advocates in Europe want to push effluent discharge for AOX down to 1.1 kg a ton. Right now it's 0.17. And there are places, I think, in the Nordics where the number is actually lower. But a study done by folks in the EU said that if they go to 0.1, there's only 38% of the mills, basically 4 out of 10, that can make it. So that means 6 out of 10 mills cannot meet those permit limits today. So they're going to have to do something different. The environmental side, the mills are comfortable. You're probably comfortable. I have no problem with my AOX discharge permit today, but we know that public perception writes public policy. And we know that the public is pushing their governments to write stricter and stricter environmental policy. So permits will change. Corrosion, plant life cycle, rust never sleeps. CO2, if any of the CO2 gases make it out and they're fugitive, they're going to react with water, they're going to create hypochlorous acid, and they're going to corrode anything that they can. So there's a lot of life cycle maintenance that has to happen. The equipment itself, sulfuric acid requires very specialized equipment. Obviously, we talked about the generator itself being titanium. And even FRP, the fiberglass reinforced plastic, has issues. In some mills, the mill that I came from, those costs became so much, and we had a couple of instances of issues with leakage that we actually replaced with titanium, which is extremely expensive, but is really the only way to get out of the wear and tear on FRP. And safety, last but not least by any means, is probably one of the most overlooked things when we look at using CO2. CO2 generators themselves are very well designed and they're very well managed. They have very nice DCS systems on them, but that's only part of the system. What about your storage tanks and supply lines? What about your destructive scrubber systems? Have you ever had a green plume coming off because your scrubber is not operating properly? What about high residuals in the bleach plant? And what about stock spills with high residuals? An incident in North America, I don't know, 3 or 4 years ago, put several people in a hospital when a washer vat overran a terminal D stage. The stock was green, it had a high residual, and the gas forced a bunch of people into the hospital with respiratory trouble. Fortunately, nobody was killed, but a lot of people were hurt. And then there's the hazmat unloading. We're using sulfuric acid, we're using methanol, we're using chlorate. Every time you have to unload a transport, there is a potential for an exposure. So if you can use a technology, say a bleaching enzyme, and you can reduce your CO2 by 20%, that also means that you're reducing the number of cars, the number of transports that you have to be opening up and putting into your system. To me, that's a very valuable thing to consider, because all systems are very well managed, but we're still managed by people, and they can and do fail. The best defense is to limit exposure. Less CO2, less residuals, less unloading of chemical transports, all of these things lead to a much lower exposure rate. None of these things are ever figured into the costs. And a 20% CO2 reduction, that's worthwhile. That's 20% less cars to unload. So remember those numbers to finish it up. The 1.58, Yeah, that's the theoretical kg of sodium chlorate to produce a kg of chlorine dioxide. The 21, you know where I'm going with this. That's the megajoules minimum to make a kg of ClO2. And the 0.1, do you remember? That's the AOX suggested permit limits for mill effluent in Europe today. So with that, in the future, when you look at new bleaching technology such as enzymes, or you're looking at retrofitting a plant to go TCF, make sure that you're not underestimating the cost of ClO2, and make sure that you're also including all of the sustainability and safety costs that are related to ClO2. So I'd like to thank you for your time. I'd like to thank Debbie French and Claudette Folks from Buckman. They helped me put this slide package together. They do a very nice job of formatting. You can always invited to come to our website, buckman.com, or you can contact me via email. There's my email addresses below. We do webinars quite frequently, and our local Buckman reps would be more than happy to invite you and point you to the sites, because we'll have webinars on a lot of things about pulp, tissue, packaging, water. This is what we do. So again, thank you for your time, and I'll open it up to questions.
Hello everyone, and thank you very much for joining. First of all, I'd like to thank the organizing committee of Tecnicelpa to having accepted that paper. And I will speak today about TCF pulp bleaching for viscose pulp production. That paper is co-authored with Professor Emile Germer. The first dissolving pulp produced with TCF bleaching was produced in 1992 at Lansing in Austria. It combined ozone, hydrogen peroxide, and oxygen. And the main target of TCF bleaching is to improve effluent quality by better managing the bleaching filtrates. Another advantage is that it does not produce any halogenated compounds. So of course, there is no IOX in the effluent, but there is also no OX in the pulp itself. So there is no OX then in the viscose fabric. Among the few pulp mills operating TCF bleaching, 5 TCF bleach plants continuously produce viscose pulp with ozone. And maybe we can look first at the chemistry. So interestingly, here you see in that table the chlorine-based chemicals and the oxygen-based chemicals. And we see that ozone reacts with the phenolic groups on the CC double bonds, while chlorine dioxide reacts on the free phenolic groups on the CC double bonds. It means that a TCF bleaching sequence combining ozone, oxygen, and hydrogen peroxide is able to remove more chromophores and chromogens from the pulp than standard TCF bleaching. Of course, as the TCF bleaching, combining ozone, chlorine dioxide, oxygen, and peroxide will be even more efficient. Two things are needed to produce ozone. It's pure oxygen and electrical energy. With electricity, we create an electrical field that breaks the oxygen molecules, and some oxygen atoms combine with oxygen molecules to produce ozone. And in fact, ozone is produced at 12% by weight concentration, meaning that we do not produce pure ozone. And to produce ozone, 1 kilogram, we need in fact 8.3 kilogram oxygen. So at the inlet of the generator, there are 8.3 kilogram oxygen, and on the outlet, there are 1 kilogram ozone and 7.3 kilogram oxygen. It requires 10 kilowatt electrical energy. And if we'd like to look at the complete needs, most of the pulp mills, in fact, produce oxygen at site with VSA plants, and production of 1 kilogram oxygen requires 0.3 kilowatt. So altogether, 1 kilogram ozone costs 12.5 kilowatt. There are two main processes to bleach with ozone. Here you see the medium consistency ozone bleaching stage. It's a very compact process that needs one MC pump, one or two ozone mixers, where ozone is injected under pressure at 10 to 12 bar gauge, and then one reactor and one blow tube. After that blow tube, the pulp is pumped to either a chlorine dioxide stage without any intermediate washing or a washer. At the top, you see off-gas to recirculation. It's because the off-gas leaving the pulp consists almost exclusively in oxygen, and it can be economically reused in oxygen acidification, EOP stage, or white liquor oxidation. That process is today the domining process. But there is also an ozone bleaching solution at high pulp consistency, where we need a specific press, bringing the pulp to a consistency of 38 to 42%. Then the pulp enters in a screw reactor, where it stays 1 minute, and it falls down in an extraction stage after dilution, where it needs only 5 minutes for the extraction. The benefit of that process is that in 5-10 minutes, you can replace much longer D0 EOP stages. Ozone is applied at the beginning of the bleaching sequences for TCF and ECF. But depending on the cooking process, it is used in the case of sulfide pulp mainly for bleaching, while in the case of kraft pulp, it's used mainly for viscosity control for dissolving pulp. Another benefit is that ozone is very reactive against extractives, so it improves the pulp cleanliness and it reduces very strongly the need for pitch control chemicals. But let's speak about kraft pulp, which is of course the main application today. So in the case of dissolving pulp production, the main target of ozone is to control the viscosity. And actually it's done automatically by implementing a mathematical model where the system, according to parameters measured online, will adjust the ozone demand. And ozone can be adjusted very quickly in seconds, because since ozone generation is managed through electricity, we can produce more or less ozone just by changing the electrical input. So ozone generation is very reactive, and it's how we can accurately control the viscosity. Here are some results. So you see some industrial results on sulfide pulp. And with only 2 kg ozone on 11 kg peroxide, it's possible to deliver an excellent dissolving pulp after sulfide cooking on a short bleaching sequence, EOP-ZP. Here I show you some lab results coming from a pulp mill that was bleaching with CEH and that investigated in the lab 2 TCF bleaching sequences, one with ozone, one without. And we see that with ozone, only 4.5 kg ozone per ton were needed and 10 kg peroxide per ton were needed. It's much lower than without ozone. And here we can clearly see that ozone saves, each kilogram ozone saves 6.7 kg caustic soda and 4.4 kg peroxide. So it's not only that ozone allows you to reach the full brightness, but it allows you saving quite important amounts of money. Concerning kraft pulp, here are some results. And again, we see a very short bleaching sequence, AZQP, where in fact the A stage is a short stage of 50 minutes at 60 degrees C. So it's more for the control of transition metals. And that short bleaching sequence needs only 3 kg ozone and 8 kg peroxide. So you see, we are always in that range of 2 to 4 kg ozone and around 10 kg peroxide. Here are some lab results where we compared a very short bleaching sequence with only one washer, ZQP, versus the standard ECF bleaching sequence DEOP-DP, and a ZECF bleaching sequence ZD-EOPD. And we see that with only 4 kg ozone and 7 kg peroxide, it was possible to reach the target. In comparison, we see that the ZECF bleaching sequence with 5 kg ozone, 3 kg chlorine dioxide, and 3 kg peroxide is so efficient that actually the brightness was not controlled and reached 94. So it means as well that a ZECF bleaching sequence is very competitive against a standard ECF bleaching sequence. So it's possible to produce dissolving pulp with a very short DCF bleaching sequence. But in the case of swing mills, producing in campaigns dissolving pulp on paper grades, it's interesting to have a longer bleaching sequence. There are two swing mills operating ozone at high consistency. And one example is DZOPD. And one interesting aspect of that bleach plant is that it can run TCF, where the first D stage is a hot, and the last stage is a peroxide stage. So it's possible to produce TCF dissolving pulp, but also TCF BEKP, as you're used to do in Portugal. But there are also 4 mills operating ZD-EOPD to produce dissolving grades on paper grades. And actually, that's the most efficient bleaching sequence available. It allows to produce dissolving pulp, hardwood paper grades, softwood paper grades on market pulp. Of course, a strong benefit of TCF bleaching is that we have no LOX, and we can significantly reduce the COD discharge by recycling the bleaching filtrates. There is no OX in the final product. And by implementing TCF bleaching, it's possible theoretically to operate a green chemical island. The green chemical island concept is that we can produce all the bleaching chemicals at site in the pulp mill with only air and water. So hydrogen is produced by water electrolysis, and from that hydrogen, mixing it with air, we produce some hydrogen peroxide. With air, we produce oxygen, and with oxygen, we produce some ozone. And all these 3 processes need electrical energy, and we know that pulp mills produce green electricity. So it's possible to produce green chemicals that are produced in a very environmental way through the use of green electricity. So in conclusions, TCF bleaching with ozone and hydrogen peroxide has proved successful technically and economically. It allows for excellent pulp quality, excellent pulp cleanliness, high pulp yield, low bleaching cost, and high brightness. Of course, effluent quality is significantly improved. And to have sustainable bleaching production of viscose pulp, it's possible for pulp mills aiming to produce dissolving pulp and paper grades to bleach with ZD EUPD or ZDP if operating a ozone at high consistency pulp. In the case of BKP and viscose grades, AZP is a very effective bleaching sequence. And for pulp mills producing only dissolving pulp, then a very short bleaching sequence, ZQP, with only one washer, is the very efficient and cheap solution. In the case of sulfide pulp, then EOP-ZP is the standard. So, dear colleagues, thank you very much for your attention, and I will be very happy to answer your questions now or later on by email. Do not hesitate sending me an email. I will answer. Thank you very much again.
Hello everyone. My name is Janne Vehmaa and I'm the technology manager in Henriques Fiberline business. I'm located in the Kotka and my responsibility is washing, screening and bleaching and oxygen delignification applications in Henriques Fiberline. Here we can see the typical Henriques Fiberline, where is a single vessel cooking and diamond pack chip bin in the beginning. We have a brown stock washing, we have oxygen delignification and post-oxygen washing, and after the post-oxygen washing is a bleaching. And this is typical application in Henriques Fiberline technology. Here is typical Henriques Fiberline oxygen and brown stock system in Henriques Fiberline, and here we can see the brown stock washing. Then we have a drop leg and pumping to the oxygen delignification. Then there is a mixing of oxygen and caustic. Then we have a shorter reaction as a first reactor and gas removal flow discharger on the top. Then we are coming down to the second reactor where we have a oxygen mixing and steam heating to the target temperature about 100 degrees, and then we have a longer retention time second reactor, and then we are coming to the flow tank. Flow tank is a new type of flow tank which is MC consistency, and then this diluting unit in the bottom of the flow tank. We have several references about that. Then there is a screen room and post-oxygen washing in multi-stage DD washer. And from here we are using the filtrate as a wash liquid in brown stock washing. And here are the typical conditions of oxygen delignification. So we are targeting about 90 to 95 degree temperature in the first and about 100 temperature in the second reactor. Final pH is about 10, and for the low kappa reduction we are using 60 to 90 minutes retention times, and for the higher kappa reductions, especially for soft foods, we are having almost we can have almost 2-hour retention time. Alkali is about 1.5 times target kappa reduction, and final pH level is 10 to 11. And we are oxygen charge is typically 80 to 90% of total alkali charge. And here is the Henriques screen room, which is located after oxygen delignification in most of our processes. And here we can see that we are coming from this new type of flow tank, where is this flow discharger diluting, screening, PT thickeners, and here we have a multi-stage DD as a post-oxygen washer. Because we are reducing a lot of size in the screen room, we can easily send from here the knots into the cooking, but also the side reject can be sent to the cooking without any problems. If we will need to take the sides out from the process, we can understand that this process is clean, and therefore the side content, therefore the sides are easily discharged from the system. One of the key technology in Henriques oxygen delignification is the mixing. We have Holm A-mix mixer, which has been our mixing platform over 30 years nowadays. And in the normal mixer, we are testing the basic mixing phenomena with this temperature test, where the thermo elements are put surround the pipe after the mixer, and here is the typical illustration about this cold water pulse. But nowadays we can also illustrate the mixing results so that we can make the pictures. This is from the industrial process, and this is the photo after the mixing from the pulp, which goes to the reactor. With this type of systems, we can update and develop our mixing process. But when we are coming into the chemistry, we have also some new things to understand. We all know that we are using caustic and oxygen, and then we have the black liquor and post-oxygen filtrate present in our oxygen delignification, and of course also the fiber lignin. The process is generating the reaction heat, and then we have a post-oxygen filtrate where is the oxidized lignin. But very important thing is also that partially we are oxidizing the lignin into the level that there is a carbon dioxide and sodium hydroxide, so the final product is sodium carbonate. And this sodium carbonate we are sending back into the process. And now we have to understand what this application means. Here is a laboratory test about the softwood pulp, starting kappa 48.5, and the final kappa is 16.3. So the point is here, and in this testing we only use the sodium hydroxide as an alkali source. And we can see that this is final viscosity 880, and we generate 3.6 grams per liter sodium carbonate. And now when we are looking the testing, what the carbonate means, if we have a carbonate and sodium hydroxide, we are slowing the reaction so that we are not reaching the same kappa number, but also we are protecting the viscosity of the pulp during the oxygen delignification. Poor caustic is giving lower viscosity, but also the lower kappa number in the final as a final kappa. What does it mean in the mill scale? We have here single stage oxygen stage using the same soft pulp, and the clean reference stage is here. No COD added into the system from any filtrate, and we have reached the kappa 36 and the reference viscosity 1190. If we use only oxygen delignification filtrate in the oxygen stage, which include that carbonate, we are losing some kappa reduction, but we practically maintain the same viscosity during the reactions. So no effect from the O2 filter. If we combined oxygen stage filtrate and black liquor based COD, we are coming to about the same kappa reduction level, but we are starting slowly losing some viscosity in the final pulp. If we then put only the black liquor based filtrate, we are getting the lower kappa, but we are immediately losing the viscosity. So here we can see that same viscosity protection effect than in the carbonate oxygen delignification can also see in with the industrial liquors and with oxygen. Typical oxygen delignification combo of black liquor and post-oxygen filtrate. Then it's one feature what we also know is that oxygen delignification is exothermic reaction. So the old experimental shows this 9.4 megajoules per kappa unit per 80 ton pulp. And oxidizing the black liquor and fiber, we get the total heat generation. And what does it mean is that if there is a lot of variation in the heat generation, but not variation in kappa number, our washing is not working properly. And in the other hand, if this heat generation is stable, it tells that the process is stable also in the washing wise. Recent 15 years, there has also been applications when the refractometers has been put into the brownstock system, washers and surround the oxygen delignifications, and when these refractometers are used smartly, they are very useful. They can indicate the washing efficiency, they can indicate the oxygen state yield, they can indicate the dilution factor, and also the process variations, what happens, for example, to the different wood species. And these are very useful tools combined with the other instruments like kappa measurements, etc. in the modern mill. So conclusions. We understand more the mixing phenomena, and we can illustrate the mixing much more scientifically. We have better understanding about the reactions, and especially carbon dioxide and sodium carbonate is more understood. Oxygen stage can be equipped with more advanced measurement, and more data can be get from there, and then we can make more smart calculations for the over the oxygen delignification, indicating yield, etc. And then what are the benefits? More tools to react for process changes in mill operations, better data for the daily control and for the operators, but also more advanced controls for the management, and these numbers enable more automated process control systems, and also these phenomena tells also more data about the washing performance. Thank you very much.
Hello. Nice to hear from you, and I'm very impressed with your work. So I have some questions. The first one to Thomas. Is there extra COD carryover to consider by using enzymes?
Not really. It's actually a complicated question because the enzymes will create more COD. This is true, but the COD is in the form of simple sugars. So as it works its way through the effluent treatment plant, is much easier to oxidize. So the effluent discharge COD is essentially the same, and in some cases even a little bit lower. So the net effect is no.
Okay. I have another question for you. Could you go further on details costs on the enzymatic pre-treatment aiming at TCF pulp production?
Yes, what TCF, we do have an application. It's a little bit more difficult to quantify. In the ECF, it's very easy. We typically figure 15 to 20% reduction in the first stage. In TCF, it still is cost effective. I'm not sure that I'm answering the question the way you would like to, but we are commercialized on a TCF application in Europe. It works quite well, and if I remember correctly, it's about 15% on the cost again, because and that makes sense because you're treating the hemicellulose. The hemicellulose content really is essentially the same at that point. So the enzyme doesn't care after that if you're going TCF or ECF. The performance will be the same.
All right. Okay. I have another question for Alexis. And that is, what is the best bleaching sequence for TCF dissolving, both for brightness and metal content?
Yes. So hello everyone, and I'd like as well to say hello to Tom and Janne. So we don't meet physically today, but I hope we can meet again next year.
Next year,
for sure.
About your questions, what is the best bleaching sequence? It depends a bit on the raw material. Do we speak about softwood, hardwood? Do we speak about sulfite or kraft pulp? But if we consider the standard, which is kraft and hardwood, I would say probably a very short bleaching sequence, ZQP, with only one washer, can make the job. And if you want a bleaching sequence that can produce paper grades, then AZP for eucalyptus or ZD EOPD for any kind of pulp.
okay. Well, I think I don't have more questions, especially for you, Janne. I don't have questions for you.
Okay.
I have a question for Janne. With O2 delig efficiency, of course, Hexa is an issue. What are some of the best delig efficiencies you've seen for hardwood pulp?
As you say that it's very dependent on hexanuronic acid. So in that sense, if you consider that you use the factor of 10 mega equivalents as a 1 kappa unit as a hexa, and then reduce it from this kappa number, we are ending up to the situation that we can reach the lignin kappa reduction about 60-65% in the oxygen delignification, which is in the same range that what we are getting with the softwood. And it's the same thing about phenolic and non-phenolic lignin, which is then this factor which is affecting this residual lignin.
Okay, thank you.
Okay, I don't see any more questions for you, both for the three of you, and so I believe we can conclude this session. Oh, if you don't have any more questions. All right.
Okay.
Okay.
Thank you very much.
Thank you very much.
Thank you.
José.
Thank you for
Thank you very much.
Yes. All right. Thank you. Bye.
Thank you.
Bye now.
Bye.